The space between galaxies is not empty at all. It is filled with a faint, ethereal gas, a cosmic medium that serves as the unseen architect of every galaxy. This video will completely change how you see the universe by revealing how this tenuous substance dictates the birth, life, and death of galaxies. We will uncover how it fuels star formation, sculpts galactic shapes, and even records the entire chemical history of the cosmos. What if the key to understanding our own Milky Way lies not in its brilliant stars, but in the profound emptiness that surrounds it? How much of our cosmic story is written in this invisible ink? This cosmic fog is the intergalactic medium, a substance so diffuse it defies our everyday understanding of matter. If you were to reach out and try to gather a handful of it, a single cubic meter of this space would hold just a handful of atoms, a stark contrast to the trillions of billions in the air we breathe. It is composed almost entirely of the universe's most basic ingredients, hydrogen and helium, the primordial ashes of the Big Bang. Because this gas is so incredibly thin, it emits almost no light of its own, rendering it nearly invisible to our telescopes. For a long time, this presented an immense challenge. How do you study something you can barely see? The answer lies not in looking for the gas itself, but in observing how it interacts with the light that passes through it. This faint, all-pervasive medium is not a minor component of the cosmos. It is, in fact, the most common form of ordinary matter, the stuff you and I are made of in the entire universe. All the stars in all the galaxies, for all their brilliance, are just a small fraction of what is actually out there. The true bulk of normal matter exists in this vast, invisible web. To grasp its influence, we first need to understand its fundamental properties, its temperature, its density, and how it is woven into the fabric of space. This is not a uniform mist, but a structured ecosystem with its own hot and cold regions, its own rivers and deserts. Peeling back the layers of this cosmic fog reveals it as the ultimate reservoir, the source from which every galaxy first condensed and drew its breath. But to move from knowing it exists to truly mapping its hidden architecture requires a special kind of vision, a way to see the unseen. Astronomers peer into this cosmic fog using tools that feel like something from a detective novel. Since the gas itself emits almost no light, they cannot simply point a telescope and take a picture. Instead, they look for the shadow it casts on the universe's brightest beacons. The most powerful of these beacons are quasars, the intensely luminous cores of distant galaxies, fueled by supermassive black holes. Think of a quasar as a brilliant lighthouse shining from the edge of the observable universe. Its light travels for billions of years before finally reaching our telescopes. During that immense journey, it passes through countless clouds of intergalactic gas. And each cloud leaves a mark. As the quasar's light pierces these wisps of hydrogen, the gas absorbs a very specific color, a particular wavelength of light. The result is not a single dark line, but a whole spectrum of them. When astronomers spread the quasar's light into a rainbow of colors, they see a barcode of missing lines, a pattern so common it has a poetic name, the Lyman Alpha Forest. This forest of absorption lines is far more than just a pretty pattern. Each line is a data point. Its width can tell us the temperature of the gas cloud that created it. Its depth reveals how dense that cloud was. And if the line is shifted slightly, that tells us how fast the cloud was moving relative to us. It is a complete cosmic medical chart, written in light. Other methods add to this picture. Specialized instruments can sometimes detect the faint glow of the gas itself in ultraviolet or X-ray light, a whisper of emission against a dark sky. And when direct observation falls short, physicists create vast digital universes inside supercomputers. These sophisticated simulations follow the laws of physics to model how this primordial gas should behave. allowing us to test our theories against the shadows we see. Together, these techniques transform an invisible medium into a detailed, three-dimensional map of the largest structures in existence. We can now trace the rivers and voids of this cosmic web. But to truly understand its role, we must travel back to the very dawn of time, to the moment this universal reservoir was first created. The very first breath of the universe was a hot, dense wind of pure energy. In those initial moments after the Big Bang, the cosmos was an opaque sea of fundamental particles, a chaotic blaze where not a single atom could hold together. Then, over a few 100,000 years, a profound transformation occurred. The universe expanded and cooled just enough for protons to capture electrons, forging the very first atoms of neutral hydrogen and helium. The result was not a brilliant light, but a deep and silent fog. This was the beginning of the intergalactic medium, a pristine and uniform veil of gas that settled over the entirety of existence. We call this era the Cosmic Dark Ages, a time of profound stillness before the first star ever flickered into being. There were no landmarks, no sources of light, just this vast, quiet reservoir of potential. Yet, this primordial gas was not perfectly smooth. Imprinted upon it were the faintest of fingerprints, tiny ripples in density that were echoes of the universe's violent birth. These quantum fluctuations, smaller than one might ever conceive, were the cosmic seeds. Slightly denser patches of gas possessed just a little more gravitational pull, slowly drawing in the material from their surroundings over millions of years. This pristine hydrogen and helium, the universe's original substance, was the only raw material available. Every galaxy, every star, every planet, and every one of us would eventually be built from this same ancient stock. For a long cosmic moment, this tranquil sea simply was. But a storm of light was coming, an event so colossal it would tear this primordial fog apart and set the stage for everything to come. This tranquil cosmic sea could not last. A new kind of dawn was breaking, one forged not in gentle light, but in the violent birth of the very first stars and galaxies. Their emergence triggered a universal revolution, an event we call the Epoch of Reionization. For the first time, the darkness was pushed back by brilliant, searing ultraviolet radiation. This intense light did not simply illuminate the fog, it tore it apart. Photon by photon, the radiation blasted electrons away from the nuclei of the neutral hydrogen atoms that filled the cosmos, reionizing the gas and fundamentally changing its character. Think of it as a great thaw, where a solid, opaque sheet of ice is transformed back into a transparent, bubbling liquid. The universe was being remade from the inside out. This phase change had profound consequences. Light, which had been scattered by the neutral fog, could now travel freely across vast distances, clearing the cosmic stage for the brilliant show we see today. But this liberation came at a cost. The energy pouring out from those first stellar nurseries heated the surrounding gas, giving it a kind of thermal pressure. This heat acted as a powerful brake, making it much harder for the gas to collapse under its own gravity to form new, small galaxies. The formation of countless dwarf galaxies was effectively suppressed, permanently altering the hierarchy of cosmic structure. Around every cluster of early stars and galaxies, immense bubbles of ionized gas began to form like clearings in a vast forest. These bubbles grew and merged, their edges sculpting the distribution of the remaining neutral gas. This was not a gentle process, but a turbulent, chaotic restructuring of the cosmos itself. The legacy of this ancient revolution is written into the very fabric of space, dictating where galaxies could form and how they would evolve. And from this upheaval, a grand architecture began to emerge, a cosmic web whose filaments and voids would define the universe for billions of years to come. This grand architecture is the cosmic web, the true skeleton of our universe. Think of the largest structure you can possibly imagine, and then realize it is dwarfed by this invisible framework. It is not a chaotic scattering of matter, but an organized network of breathtaking scale. At its heart lie immense knots, where thousands of galaxies swarm together in dense clusters. These clusters are connected by long, twisting filaments of gas, stretching across hundreds of millions of light years like cosmic highways. Between these threads lie the vast, empty voids, regions of profound emptiness so large they could swallow thousands of galaxies whole. And spanning these gaps are great, thin sheets of matter like the walls of a cosmic sponge. The majority of the faint intergalactic gas, the very substance we have been following, does not float freely in the voids. It is concentrated within these filaments, flowing along them like water rushing through a network of rivers. But what guides this flow? The rivers are carved by an unseen landscape, the gravitational pull of dark matter. This mysterious substance, which we cannot see directly, forms the underlying scaffold of the web. Its gravity dictates the paths, drawing the ordinary gas into the filaments and funneling it toward the waiting galaxies. A galaxy's location within this web determines its entire destiny. A galaxy isolated in a quiet void may starve, cut off from the fresh supply of gas. But a galaxy sitting at a busy intersection of multiple filaments, a cosmic metropolis, finds itself at a feast. Here, the gas flow is constant and rich, providing a steady fuel supply for furious rounds of star formation. This is why we see the most massive and active galaxies thriving in these dense hubs. They have a gravitational advantage, pulling in material from all directions. This web is not a static picture. It is a dynamic, evolving entity. Over billions of years, gravity tirelessly works, pulling more and more matter out of the voids and into the strengthening filaments. The rivers of gas grow deeper, the knots of galaxies become denser, and the entire structure becomes more defined. To truly grasp how a galaxy grows, we must follow the journey of this gas as it travels from the cosmic web, down the filaments, and finally arrives at a galaxy's doorstep, ready to be transformed. This steady inflow of cosmic gas is the lifeblood of every galaxy. Imagine a great city, its factories and homes constantly consuming resources. Without a steady stream of supplies arriving by road and rail, that city would eventually stagnate and fall silent. A galaxy operates on the same principle. It is not a closed system, but a dynamic entity constantly fed by rivers of pristine hydrogen and helium flowing in from the cosmic web. Astronomers call this process accretion, the continuous gathering of intergalactic matter. This fresh fuel is absolutely essential, because a galaxy is always spending its gas reserves to build new stars. Without this replenishment, its star-forming factories would eventually run out of raw material. But how does this fuel actually arrive? It comes in two primary forms, each with its own cosmic signature. The first is a smooth, hot, and steady rain. This is gas that has been heated as it falls into the galaxy's gravitational grasp, spreading out into a vast, tenuous halo. It arrives slowly and consistently, a gentle background infusion. The second method is far more dramatic. These are cold streams, dense rivers of gas that manage to stay cool as they travel along the dark matter filaments of the cosmic web. They punch right through the hot halo like icy underground aquifers, delivering their cold, star-ready fuel directly to the galaxy's core. The balance between these two modes of delivery is everything. A massive galaxy sitting at the heart of a crowded cluster primarily feeds on the smooth, hot rain, often by drawing in gas from its own surroundings or by consuming smaller galaxies. Its immense gravity heats the incoming gas to extreme temperatures, making it harder for the gas to cool down and form stars quickly. In contrast, a smaller, isolated galaxy is often fed by those cold, narrow streams. This direct pipeline provides a rich and efficient fuel source, allowing for vibrant, ongoing star birth. This steady diet of intergalactic material is what separates a vibrant, blue, star-forming galaxy from one that has become red and dead. A galaxy that has consumed its gas and can no longer create new stellar generations. But the journey of this gas is not over once it crosses the galactic threshold. What happens next, when this pristine fuel enters the complex ecosystem of a galaxy, determines its ultimate fate. But this incoming fuel arrives in a state of cosmic chaos. It is a hot, diffuse wind, far too energetic and spread out to simply collapse into a star. For a galaxy to build new suns, it must first tame this raw material, forcing it to cool down and condense. This transformation is the true alchemy of star formation. The key mechanism for this is radiation. As atoms and ions within the gas collide with one another, they get excited and then release that excess energy by emitting photons, little packets of light that carry the heat away into the void of space. It is as if the galaxy is sweating, releasing its thermal energy to cool itself down. But not all gas cools at the same rate. The efficiency of this cosmic air conditioning depends critically on what the gas is made of, specifically its metallicity. This term refers to the abundance of all elements heavier than hydrogen and helium. While these heavier elements are only trace contaminants, they are incredibly effective at radiating heat away. Elements like carbon, oxygen, and iron have many more complex energy levels than simple hydrogen, creating far more avenues for the gas to shed its energy and cool down rapidly. A gas cloud rich in these metals can chill into a dense, star-forming cloud millions of years faster than a pristine cloud of only hydrogen and helium. We can observe this cooling process in action within the vast halos that surround galaxies. In some massive galaxy clusters, we see evidence of cooling flows, where huge volumes of hot halo gas slowly radiate their energy and begin to sink inward toward the galactic center. In other cases, the cooling gas condenses into what we call high-velocity clouds. These are massive, dark clouds of cold hydrogen, often moving at incredible speeds as they rain down upon the galactic disk. They are the delivery trucks of the cosmos, carrying their chilled cargo directly to the star-forming factories. When this gas finally cools enough, it loses its buoyancy and sinks into the galaxy's central disk, pooling into immense, dark molecular clouds. These clouds are the stellar nurseries, the cold, dense cradles where gravity can finally overcome all resistance and trigger the birth of new stars. This entire journey from a hot, ionized wind to a cold, dark cloud is the critical bottleneck that dictates the pace of a galaxy's growth. It is the narrow gate through which all star-forming fuel must pass. Yet this journey is not a one-way street. Not all the gas that enters a galaxy succeeds in becoming a star. Some of it is violently rejected, cast back out into the darkness from whence it came. A galaxy can also fight back against its own growth. This is not a quiet process, but a violent expulsion driven by the very stars it creates. When the most massive stars reach the end of their short, brilliant lives, they die in colossal supernova explosions. These blasts, combined with the intense radiation pressure from newborn stellar clusters, generate immense galactic winds. These are not gentle breezes, but hurricanes of superheated gas that can blow right through a galaxy, carrying with them vast quantities of enriched material. This is the galaxy's own exhaust system, a powerful outflow that actively recycles matter back into the cosmos. This feedback loop serves a crucial purpose. By ejecting this gas, the galaxy is essentially turning down the thermostat on its own star-forming factories. It removes the very fuel needed to make the next generation of stars, preventing a runaway boom that would consume all the available gas in a single, furious burst of creation. Without this self-regulation, galaxies would burn out in a cosmic flash, leaving behind only stellar embers. But the impact of these outflows reaches far beyond a single galaxy's borders. The gas that is violently expelled is not the same pristine hydrogen and helium that flowed in. It has been transformed. Inside the furnaces of stars and in the heart of supernova, hydrogen and helium are fused into heavier elements: carbon, oxygen, iron, all the building blocks of planets and life. This polluted, metal-rich gas is then catapulted out into the vast intergalactic medium. The pristine reservoir of the cosmic web is forever changed by this contamination. Where once there was only simple hydrogen, there are now traces of these heavier elements, a form of cosmic pollution that carries the signature of stellar life and death. This enrichment has a profound consequence for the future of other galaxies. As we learned, gas laced with metals cools down far more efficiently. So when this enriched material eventually falls back onto a different galaxy, perhaps in a different cluster trillions of years from now, it will be primed to collapse and form stars more easily than the primordial gas ever could. The violent death of stars in one galaxy can therefore set the stage for an accelerated birth of stars in another, a legacy written in the chemical makeup of the cosmos itself. This grand cycle of expulsion and enrichment forces us to look at the universe not as a collection of isolated islands, but as a single, interconnected ecosystem. The story of a single galaxy is written not just by the gas it pulls in, but by the material it gives back. This cosmic ledger is written in the language of elements. For billions of years, the pristine gas of the early cosmos has been slowly but surely polluted, not by any industrial accident, but by the very life cycles of the galaxies themselves. This process of chemical enrichment is a slow and relentless transformation of the universe's fundamental character. Where once there was only the primordial simplicity of hydrogen and helium, there is now a faint but measurable trace of heavier substances: carbon, oxygen, iron, the very stuff of planets and life. Astronomers call this level of contamination metallicity, a term that encompasses all elements heavier than the original two. By measuring the metallicity of the faint intergalactic gas, we are essentially reading a history book. Each atom of oxygen found drifting between galaxies is a tiny fossil, a relic from the core of a long-dead massive star that lived and died billions of years ago. This is the integrated star formation history of the entire cosmos, tallied not in light, but in chemical residue. The distribution of this pollution tells its own story. It is not spread evenly like a thin coat of paint. In the dense, crowded metropolises of galaxy clusters, the intergalactic medium is a rich chemical soup, heavily seasoned by eons of stellar winds and supernova from thousands of member galaxies. In contrast, the vast, empty voids between the cosmic web filaments remain almost pristine, their gas barely touched by the alchemy of stars. This is where the universe's original composition is best preserved. This contamination has a profound and active consequence. As we learned, gas that contains even a tiny fraction of these heavy elements cools down with incredible efficiency. So, the very act of polluting the cosmic reservoir makes that fuel far more potent for the next round of galaxy building. A galaxy that forms today from this pre-enriched gas has a significant head start over one that formed in the early universe from pure hydrogen and helium. The gas is already primed to cool, condense, and collapse into stars more quickly. The faint intergalactic gas, therefore, is far more than a passive reservoir. It is a dynamic, evolving substance, a cosmic ledger that meticulously records the chemical output of every generation of stars. And this enriched gas does not stay adrift forever. It can be swept up by the gravitational pull of a new galaxy, reaccreted to fuel a new cycle of stellar birth. The death of one stellar generation literally fertilizes the cradle of the next. But what is the immense, unseen hand that guides this entire cosmic dance, that directs the flow of this enriched gas, and dictates the grand architecture of the web itself? The answer lies in the most mysterious substance of all. This invisible stage is built by dark matter, the universe's most enigmatic substance. Though we cannot see it, touch it, or even directly detect it with our instruments, we know it is there because of its immense gravitational pull. It is the hidden puppeteer, and the faint intergalactic gas is the dancer, following every contour of the stage it cannot see. Dark matter makes up the overwhelming majority of the universe's mass, a staggering 5 times more than all the ordinary matter, the stuff of stars and planets and us combined. Its gravity is the primary force sculpting the grand cosmic web, carving out the deep wells and the vast filaments that define the largest structures in existence. The gas does not decide where to flow. It simply falls into the gravitational valleys that dark matter has already carved, pooling in the filaments and knots of this invisible lattice. The very nature of this dark substance, its fundamental properties, dictate the texture of the cosmos. If dark matter is what we call cold, meaning its particles move relatively slowly, it readily clumps into smaller, denser halos. This provides numerous small gravitational anchors, allowing gas to fragment efficiently and seed a multitude of small, early galaxies. But if dark matter were warm with faster-moving particles, it would resist clumping on small scales, potentially suppressing the formation of the smallest dwarf galaxies and altering the entire early universe. This partnership is the foundation of all structure. Without dark matter's relentless gravitational pull, the primordial gas would have remained a nearly uniform, featureless haze, never collapsing into the brilliant pinwheels and glowing ellipticals that fill the night sky. Dark matter built the stadium, and the gas is the player whose performance we watch. This fundamental relationship explains why galaxies are not scattered randomly, but are instead strung along the luminous threads of the cosmic web. Yet, even on this universal stage, not every performance is the same. The way a galaxy consumes its gaseous fuel creates a dramatic divergence in its life story, leading to the stunning variety of galactic forms we observe. This relationship between a galaxy and its fuel supply writes the entire story of its life, a story visible in its very shape and color. Take a majestic spiral galaxy like our own Milky Way. It is a portrait of sustained creation, its brilliant blue arms tracing a pattern of ongoing star birth. This vibrant existence is fueled by a steady, efficient delivery system, a cold-mode accretion of gas that flows directly into its rotating disk. This constant supply of fresh, cool hydrogen provides the raw material for new stellar generations, keeping the spiral alive and glowing. Now, shift your gaze to a massive elliptical galaxy. It presents a completely different picture, a vast reddish sphere of ancient stars. This is a galaxy that has largely stopped forming new suns, a cosmic retirement community. It often resides at the crowded heart of a galaxy cluster, submerged in a seething ocean of hot gas. In this environment, any new gas that tries to fall in is heated to such extreme temperatures that it struggles to cool down and condense. The galaxy's own immense gravity creates a stifling hot atmosphere that effectively shuts down its primary fuel line, leaving it to glow with the fading light of its old stellar population. Then there are the dwarf galaxies, the small, fragile towns of the cosmos. With their shallow gravitational wells, they have only a weak hold on their gaseous resources. A close pass by a larger galaxy, or even the simple pressure of moving through the dense intergalactic medium in a cluster, can easily strip this fuel away. It is a cosmic version of a strong wind blowing away a small campfire's supply of kindling, leaving it to smolder and eventually go out. The availability and careful processing of intergalactic gas is the primary author of this galactic diversity, directly dictating a galaxy's structure, its color, and its entire history of star formation. For these vulnerable dwarf galaxies, the greatest threat often comes from their surroundings, a process of environmental stripping that can leave them completely barren. The force of this environmental theft is called ram pressure stripping, and it is one of the most brutal interactions in the cosmos. Picture a galaxy not as a static island, but as a ship sailing at incredible speed through the thin, superheated gas that fills a galaxy cluster. The resistance it feels is the intergalactic medium pushing back, a cosmic headwind of immense power. This is not a gentle pressure, but a gale force that can rip the galaxy's own gas right out of its gravitational grasp. The most vulnerable component is the cold, dense hydrogen fuel that resides in the galaxy's disk, the very material it needs to form new stars. We can actually see this violence in action. Telescopes have captured stunning images of galaxies with long, shimmering tails of gas streaming behind them, like cosmic hair blown back by a relentless wind. This stolen material is not lost to the void. It is donated back to the intergalactic medium of the cluster, enriching it further. For the galaxy, however, this is a catastrophe. Its primary fuel supply is being severed. The vibrant blue regions of active star formation begin to fade, and over time the galaxy transforms. It becomes a red and passive system, a place where the stellar birth rate plummets toward zero. This quenching effect is ruthlessly efficient against smaller, dwarf galaxies. Their gravitational grip is simply too weak to hold on against the onslaught, and they are often completely stripped of their gas, left as dark, starless husks of mostly old stars and dark matter. This process provides one of the clearest direct links we have, a visible demonstration of how the faint, all-pervasive gas between galaxies can reach out and directly strangle a galaxy's future. Yet, for galaxies that manage to hold on to their fuel, the intergalactic medium can exert its influence in a slower, more insidious way. The raw power of gravity itself can overheat a galaxy's fuel supply. When vast rivers of intergalactic gas fall toward a truly massive galaxy cluster, they do not simply flow in smoothly. They plunge into the deep gravitational well created by the cluster's immense dark matter halo, accelerating to incredible speeds before crashing into a wall of their own making. This collision generates a cosmic traffic jam of unimaginable scale, a phenomenon known as virial shock heating. The incoming gas is compressed and heated so violently that its temperature soars to millions of degrees, transforming it into a seething, diffuse atmosphere that envelops the entire cluster. This hot halo is not just an interesting side effect, it is a powerful thermostat. For the central galaxies trapped inside, this is a profound problem. The gas they need to form stars is now too hot and energetic to cool down and condense. The very act of drawing in fuel on such a grand scale has effectively shut down the primary delivery line for star formation. We can actually see this process at work. The superheated gas glows not in visible light, but in high-energy X-rays, and our space-based telescopes detect this brilliant, ethereal fog surrounding the universe's largest galactic metropolises. This heating mechanism is a crucial form of cosmic self-regulation. It ensures that the most massive galaxies cannot simply hoard all the available gas and grow without limit, explaining why we do not see galaxies 100 times larger than our own Milky Way. It is a balancing act between the relentless pull of gravity and the physical limits of cooling. But this balance is not left to chance alone. Another, even more violent actor waits in the heart of nearly every large galaxy, one capable of flipping the thermostat on and off. This final actor in the cosmic drama is the supermassive black hole, a silent titan lurking at the center of nearly every large galaxy. When this black hole actively feeds on the surrounding gas, it does not consume quietly. The infalling matter swirls into a blazingly bright disk, transforming the core into an active galactic nucleus, or AN, one of the most energetic phenomena in the universe. The power released is almost incomprehensible, often outshining every star in the galaxy combined. But this is not just a brilliant light show. A significant portion of this energy is channeled into narrow, relativistic jets that shoot out for thousands of light years and into vast, spherical winds that blast through the galactic interior. These outflows carry a staggering amount of energy directly into the halo of hot gas surrounding the galaxy, and even further out into the intergalactic medium itself. This is AGN feedback, a cosmic regulatory mechanism of breathtaking precision. The energy injected by the black hole heats the surrounding gas, preventing it from cooling down and falling back into the galaxy to form new stars. It is as if the galaxy's central engine has its own thermostat, one that can flip on with tremendous force to prevent the system from overheating with new stars. This process solves a major cosmic mystery. For a long time, astronomers wondered why the largest elliptical galaxies, sitting in pools of incredibly hot gas, did not simply draw in that fuel and form trillions of new stars, growing to impossible sizes. The answer is the AGN. When cooling gas begins to flow inward in a massive cooling flow, it eventually feeds the central black hole. The black hole awakens, and its explosive output heats the surrounding gas, shutting down the cooling flow and thus starving itself of further fuel. This creates a tight feedback loop, a self-regulating cycle where the growth of the black hole is intrinsically linked to the rate of star formation in the entire galaxy. The faint intergalactic gas is the crucial medium in this entire process. It serves as the primary fuel source for the black hole's feast, and it is also the substance through which the black hole's energetic feedback is disseminated, its heat echoing across the galactic environment. This intricate dance, a balance between the inward pull of gravity, the outward push of black hole energy, and the delicate cooling properties of the gas, is a cornerstone of our modern understanding of the cosmos. It weaves together the fate of the largest structures with the behavior of the most extreme objects. To see this grand cycle in action, we must learn to read its history, to observe how these fundamental relationships have shaped the universe from its earliest epochs to the present day. Our telescopes are time machines, reading the universe's autobiography as it was written across the ages. Each distant quasar is a chapter marker, its light a messenger from a specific era in cosmic history. By analyzing the absorption lines in the Lyman alpha forest from quasars at different distances, astronomers can construct a timeline of how the intergalactic medium itself has transformed. The further back we look, the more the story changes. In the youth of the cosmos, the gas was far denser and largely neutral, a thicker fog that filled the spaces between the first emerging structures. Over billions of years, that fog has been steadily clearing and heating, becoming more diffuse and more thoroughly ionized by the collective radiation of countless galaxies. We are witnessing the long tail of the Epoch of Reionization, a process that did not simply end, but has continued to shape the medium in more subtle ways. At the same time, the chemical signature of the gas tells its own tale of progress. The metallicity of this vast reservoir has climbed, however slowly, from virtually zero to a measurable trace. This is the accumulated exhaust from generations of stars, a pollution that marks the universe's growing chemical complexity. Even the texture of the gas has evolved. Its temperature and its clumpiness, the way it gathers into clouds and filaments, are not constant. These properties reflect the changing influences of cosmic events, from the initial blast of reionization to the later, more localized heating from active galactic nuclei. This temporal view is our ultimate test for the entire narrative of cosmic evolution. It allows us to ask whether our models correctly predict how the rules of galaxy formation have shifted from the cosmic dawn to the present day. Are we right about how gas cools, how feedback regulates growth, and how the cosmic web assembled itself? The answers are written in the fading light of the most distant quasars, but to read them clearly, we need ever more powerful eyes on the sky. For decades, our vision of this cosmic ecosystem was transformed by a single eye in the sky. The Hubble Space Telescope did not just show us galaxies, it showed us the space between them. Its unique position above Earth's atmosphere allowed it to see in ultraviolet light, the precise wavelength where the Lyman alpha forest casts its shadows. Hubble's deep, long stares at distant quasars were not merely taking pretty pictures. They were conducting a cosmic census, gathering millions of those absorption lines to painstakingly map the distribution and physical state of the intergalactic gas. Its legendary deep field images, revealing thousands of galaxies in a patch of sky the size of a grain of sand, also gave us the context for this gas, showing us the galactic neighborhoods embedded within the cosmic web. Yet, as revolutionary as Hubble has been, it is like a powerful but aging explorer, pushing against the very edges of its vision. It could see the cosmic web, but the earliest chapters of the story, the time of the very first galaxies and the final act of reionization, remained just beyond its grasp. The next generation of observatories is now taking the stage, each with a specific role in this grand investigation. The James Webb Space Telescope is our ultimate time machine, its infrared eyes designed to peer back to the cosmic dawn. It can directly observe the light from the infant galaxies that first ionized the universe, and study the primordial gas that was just beginning to be polluted by those first stellar generations. Meanwhile, here on the ground, a new class of giants is rising. Extremely large telescopes, with mirrors spanning the width of a tennis court, will use their immense light-gathering power to dissect the faint glow of intergalactic gas with stunning precision, allowing us to trace its dynamics and flow in ways previously impossible. And floating in space, X-ray observatories continue to chart the searing hot component of the intergalactic medium, the multimillion-degree plasma that fills galaxy clusters and reveals the immense energy of cosmic collisions. Each new facility opens a different window, providing a fresh perspective on the same faint, all-pervasive substance. But this flood of new, high-definition data presents its own profound challenge. How do we make sense of it all? How do we test if our understanding of cosmic evolution is correct? The answer lies not only in the sky, but inside the world's most powerful supercomputers. These digital universes unlock the secrets our telescopes cannot directly see. To understand the faint dance of intergalactic gas, astrophysicists build entire cosmos inside some of the world's most powerful supercomputers. These are not simple animations, they are full physical laboratories, governed by the strict laws of gravity, hydrodynamics, and radiation. Projects with names like Illustris TNG and EAGLE start with a near-uniform box of virtual dark matter and gas, a digital replica of the early universe. Then they press play. Over millions of CPU hours, the simulation calculates how every particle interacts, tracing 13 billion years of cosmic evolution in a matter of weeks. Within this virtual space, you can follow a single wisp of intergalactic hydrogen as it flows along a dark matter filament, crashes into a growing galaxy, gets heated by a supernova, and is then ejected back out into the void. You can watch a supermassive black hole at a galaxy's heart flare to life, its energetic jets punching into the surrounding gas and shutting down star formation across an entire virtual cluster. This is the only way to run experiments on a cosmic scale, changing one variable, like the strength of stellar winds, to see how it alters the entire population of galaxies that emerges. The ultimate test is a direct comparison. Scientists take the final snapshot of their simulated universe and ask a simple question: does it look real? Does the virtual Lyman alpha forest match the one we see in quasar spectra? Do the simulated galaxies have the same shapes, sizes, and colors as those we observe? When the answer is yes, we know our understanding of the underlying physics is likely correct. When the simulation fails, it points directly to a gap in our knowledge, a missing piece of the cosmic puzzle. One of the most significant triumphs of this approach has been its role in solving a deep cosmic mystery known as the missing baryon problem. For all the brilliance of the stars and galaxies we can see, the universe seemed to be suffering from a profound accounting error. When cosmologists calculated the total amount of ordinary matter that should exist, based on the pristine blueprint of the cosmic microwave background, their numbers came up short. A vast portion of the universe's normal stuff, the baryons that make up every atom, every planet, and every one of us, was simply missing from the present-day census. This was the missing baryon problem, a cosmic whodunit that baffled astronomers for years. Where could an entire third of the universe's ordinary matter simply vanish? The prime suspect, it turns out, was hiding in plain sight, or more accurately, in near darkness. The leading theory pointed directly to the faint intergalactic gas, but not in its cool, calm form. The missing matter was thought to be locked away in a specific, elusive state known as the warm-hot intergalactic medium, or the WIM. This is not the cool gas of the cosmic rivers or the searing plasma of galaxy clusters, but a vast, tepid ocean of million-degree gas stretching through the low-density regions of the cosmic web. This gas is so incredibly diffuse and so hot that it barely interacts with light, making it nearly invisible to direct observation. It is the universe's ultimate camouflage. To find it, astronomers had to become cosmic detectives, looking for the faintest of clues. One method is to search for the whisper-thin emission of X-rays this superheated gas produces, a signal so weak it drowns in the background glow of the cosmos. Another, more ingenious technique looks for the ghostly imprint the WIM leaves on the most ancient light we can see. As the cosmic microwave background radiation travels across the universe, it occasionally passes through these vast filaments of hot gas. The WIM electrons scatter the microwaves, creating a subtle, shimmering distortion in the light, a sort of cosmic mirage that betrays the hidden matter's presence. Finding this missing mass is about more than just balancing a cosmic ledger. It is the final step in confirming our fundamental understanding of how the universe assembled itself from the Big Bang to the present day. It completes the inventory of the ordinary stuff of creation, confirming that what we see in the infant universe truly evolved into the web of galaxies we see today. The hunt for the WIM is now a primary goal for the next generation of X-ray observatories and microwave telescopes, each one designed to be sensitive enough to see this universal ghost. Solving this mystery would finally close the case, revealing that the missing matter was never truly gone, but simply waiting, a vast and hidden component of the cosmic ecosystem that has been shaping galaxies all along. These future detectives are already taking shape in laboratories and on drawing boards around the world. The quest to find the universe's missing matter is fueling missions of staggering ambition. The European Space Agency's planned Athena X-ray Observatory, for instance, will possess a vision so acute it can finally map the faint, searing glow of the warm, hot intergalactic medium, tracing the hidden arteries of the cosmic web in exquisite detail. On another front, powerful space telescope concepts like LUVOIR or HAB-X are designed to perform cosmic spectroscopy on an industrial scale. Instead of studying one quasar at a time, they could analyze the Lyman alpha forest for thousands simultaneously, creating a three-dimensional census of the cosmic fog with resolution we can scarcely imagine today. And while some look to the hot and the ionized, others are tuning their instruments to the faintest possible radio whisper. New generations of advanced radio telescopes are listening for the elusive signal of neutral hydrogen from the cosmic dawn, a ghostly echo from the time before the first stars ever ignited, hoping to capture the universe in its original, pristine state. These are not merely incremental improvements. They represent a fundamental shift in our capabilities. The next decade promises to transform the faint intergalactic medium from a subject of inference into one of direct, high-definition observation. We will not just find the missing baryons, we will watch them flow. We will trace the complete life cycle of galactic fuel, from its initial condensation in the cosmic web, its journey into a galaxy, its transformation inside stars, and its eventual explosive return to the void. This grand cosmic cycle, the breathing of the universe itself, will be laid bare. And this profound understanding of how galaxies live and breathe connects to a question much closer to home. The same processes that govern the flow of gas also dictate a galaxy's habitability. The rate of star formation, the frequency of supernova, the very distribution of heavy elements necessary for planets and life, are all direct consequences of this delicate balance. By unraveling the mysteries of the faint intergalactic gas, we are ultimately learning the universal rules that determine where life might find a foothold in the cosmos. This cosmic cycle of gas and galaxies is ultimately a story about our own origins. The faint intergalactic medium does more than just build galaxies. It directly sets the stage for the possibility of life itself. The rate at which a galaxy gathers this fresh fuel dictates its entire star formation history. And that history is written in the elements that make up our world. Inside the nuclear furnaces of stars, simple hydrogen and helium are forged into heavier atoms. When those stars reach the end of their lives, they expel this newly created material, enriching their galactic environment with carbon, oxygen, iron, and all the other essential ingredients for rocky planets and the chemistry of life. A galaxy with a steady, well-regulated supply of intergalactic gas is a stable stellar ecosystem. It avoids the violent, short-lived bursts of star formation that would flood planetary systems with lethal radiation from frequent supernova. Instead, it can foster long-lived, quieter stars like our own Sun, providing a stable energy source for billions of years, a timescale long enough for biological evolution to run its slow, miraculous course. The enrichment of the intergalactic medium itself adds another layer to this cosmic preparation. A new galaxy forming today does not start from pure, primordial hydrogen. It condenses from gas that has already been seeded with these heavy elements from long-vanished stellar generations. This means that from its very birth, such a galaxy is preloaded with the raw materials for terrestrial planets. The cosmic cycle of gas, from the cosmic web into galaxies and back out again, is therefore a grand recycling program that continuously enriches the universe with the building blocks of complexity. The faint rivers of gas flowing in the darkness are more than just galactic fuel lines. They are a fundamental part of the narrative of life, connecting the vast architecture of the cosmos directly to the conditions on a small, rocky world. Yet for all we have uncovered about this intricate dance, profound mysteries about the faint, intergalactic gas continue to challenge our understanding. Even with all we have learned, the faint intergalactic gas guards its deepest secrets closely. The hunt for the warm, hot intergalactic medium, the WIM, is a perfect example. We have strong theoretical reasons to believe this tepid ocean of million-degree gas holds the universe's missing matter, but confirming its precise physical state remains a monumental challenge. Is it a smooth, diffuse haze, or is it gathered into wispy, tangled filaments? Catching its faint whisper against the cosmic background glow is one of the most difficult tasks in modern astronomy. Another puzzle lies in the resilience of cold streams. Our simulations show these rivers of cold gas flowing into massive galaxies, but how do they survive the journey? The hot halo surrounding a large galaxy should, in theory, evaporate or disrupt these delicate filaments long before they reach the galactic disk. Their continued existence suggests there is a fundamental piece of physics, perhaps involving magnetic fields or intricate turbulence, that we do not yet fully understand. Then there is the question of the universe's great awakening, the Epoch of Reionization. We know it happened, but the exact sequence of events is still blurry. Did the first, faint galaxies provide most of the ionizing radiation, or were the brilliant, rare quasars the primary drivers? Unraveling this timeline is like trying to determine which candles lit a dark room first, when all we see is the fully lit space billions of years later. And threading through all of this is the ghostly influence of magnetic fields. These invisible forces are incredibly difficult to measure across intergalactic distances, yet they could be acting as a cosmic scaffolding, providing pressure and structure to the gas, guiding its flow in ways we have only begun to suspect. Each of these mysteries is a loose thread in our tapestry of cosmic evolution. Pulling on any one of them could unravel our current understanding or, more excitingly, reveal a completely new pattern. The answers will not come from a single telescope or simulation, but from a symphony of next-generation tools working in concert. This is not the end of the story, but a vibrant and ongoing frontier. The faint intergalactic gas ensures that the universe still holds profound surprises, challenging us to look deeper and think harder. These lingering questions force us to step back and ask how all these intricate pieces, from the smallest wisp of gas to the largest cosmic structure, ultimately fit together into one coherent picture of the universe. The faint gas between galaxies is a final, critical witness to the universe's birth. Its behavior provides some of the most powerful tests for our fundamental model of the cosmos, known as lambda CDM. This framework rests on the pillars of dark energy, represented by lambda, and cold dark matter. It is a grand theory, but a theory must be confronted with evidence. The intergalactic medium offers that evidence in abundance. Its distribution is not random. It perfectly mirrors the invisible scaffold of dark matter. The intricate pattern of the Lyman alpha forest, the very density of those absorption lines, acts as a cosmic scale. It can tell us whether dark matter is truly cold, made of slow-moving particles, or if it has a warmer, more frenetic nature. If dark matter were warm, its particles would move fast enough to smooth out the smallest clumps of matter in the early universe. This would leave a distinct signature, a lack of the finest filaments in the cosmic web, which would in turn make the Lyman alpha forest appear simpler, with fewer delicate absorption lines. The fact that we see such a complex, fine-grained forest strongly suggests dark matter is cold, allowing those tiny structures to form. Beyond dark matter, the history of this gas is a timeline of cosmic energy. The temperature and ionization state of the intergalactic medium record every major release of power, from the initial blast of reionization to the later, more localized heating from quasars. It is a fossil record of the universe's thermal history. By serving as a precise tracer of the underlying dark matter structure, this faint gas becomes a bridge. It connects the physics of the unimaginably large, the geometry of the entire cosmos, to the rules that govern the very small. Every observation of a quasar's spectrum is not just a measurement of gas. It is a test of our most fundamental ideas about space, time, and the contents of the universe. This grand synthesis brings us to a moment of profound reflection on our own place within this vast, interconnected system. Every single atom in your body has a cosmic passport stamped with a journey of unimaginable scale. The iron in your blood, the oxygen in your lungs, the calcium in your bones, all of it was forged in the heart of a long-vanished star. But before that star ever ignited, these very atoms were adrift in the vast, faint reservoirs of the intergalactic medium. They were primordial hydrogen and helium, cycling through the great rivers of the cosmic web, drawn into an ancient galaxy, and then swept up into a stellar nursery. Inside that star, they were fused into heavier elements, and when that star reached the end of its life in a spectacular supernova, they were expelled back out into the galactic winds, a polluting gift to the cosmos. Eventually, these now enriched particles found their way into the cloud of gas and dust that collapsed to form our solar system. We are not just living in the universe, we are a literal, physical part of its ongoing narrative. The water we drink, the ground we walk on, the air we breathe, it is all recycled star stuff, processed through the faint gas between galaxies. This realization transforms our quest from a purely scientific investigation into a deeply personal one. Understanding the influence of this faint intergalactic gas is the same as reading our own cosmic ancestry. It connects the largest structures in existence directly to our own moment of conscious awareness. We are the universe's way of looking back at itself, of contemplating its own origins and its grand interconnected flow. With this profound connection in mind, we can see that our search for knowledge is not separate from the cosmos, but a beautiful and natural expression of its own evolving story. This invisible substance is the universe's ultimate architect. Our journey confirms that this faint intergalactic gas is far from empty space. It is a primordial reservoir holding the original ingredients of creation. It acts as a cosmic delivery system, funneling fuel along invisible rivers to hungry galaxies. It is a meticulous regulator, its delicate balance between heating and cooling dictating whether a galaxy thrives or falls silent. And it is a permanent chemical ledger, recording every stellar explosion and galactic wind in an atomic script. From seeding the very first galaxies to setting the stage for planets and life, this tenuous medium is a lead character in the cosmic story. We have traced its path from the cosmic web's grand filaments, watched it be drawn into galaxies through both gentle rain and cold, direct streams, and witnessed its violent expulsion by stellar winds and black holes. We have seen how its environment can strip a galaxy bare or overheat its fuel supply. While the hunt for the warm, hot intergalactic medium and the secrets of cold streams continue, new telescopes and sophisticated simulations are peeling back the layers of these enduring mysteries. So the next time you gaze at the night sky, remember this: the profound darkness between the stars is not a void. It is a dynamic, evolving ocean, a substance that cradles the history of everything and holds the blueprint for all that is to come. Thank you for joining this exploration of the cosmos's hidden foundation. If this journey through the mysteries of space has captivated you, please subscribe for more voyages into the unknown.